welcome back to our second part of lecture 1 today. Basically of cloud computing and big data as a really introduction round. So what are the topics we face in the course at large? So it's clear that all the different terminologies are not perfectly clear to you after this call, or basically after this presentation. So the second part of this lecture today will be switching the view a little bit to big data. Now we think about terms like scalability, going maybe from a couple of terabytes to petabytes, or basically thinking about using your MP3 collection that you had at home and now shifting them to the cloud. What services could be there for you that help there? So lots of interesting challenges in the words around big data. And one of the first ones is to basically think about what is big data. It is a buzzword if you want. Some people would say it's a hoax. It depends. Of course, big data is essentially meaningless until you put a specific data repository, a specific challenge to it. And you see big data in many ways have been quoted by the general, let's say, growth of digital storage. So of course, our papers and so on are diminishing. And what we have is lots of digital storage. But what we refer to also many times is that really the kind of different projects, the different repositories, they are really growing in size. Let's say scientific data sets, they are growing very much in different directions. Now, the term big data is therefore seem to be really, motivated by the volume term, right? So storage, everything is gigabytes, and then there's the terabytes, petabytes, exabytes, what we have right now. But the interesting thing is, that's not always made it a challenge in this big data aspect. You have aspects like velocity, so how quickly comes data in. There's something like the square kilometer array, where basically this is just a terabyte of data, but it comes every second from the scientific instrument. This is a challenge. The terabyte alone, we have many, many petabytes at Jülich, at the data center, or Amazon has many petabytes, but the sheer speed of the direction of having a terabyte coming every, let's say, second in, this is a challenge with big data. And then also the variety, you see that basically like Facebook, social online media networks, they're growing in this direction, scientific data sets growing in this direction. You have a very heterogeneous nature of data these days, where of course storage has to fulfill, let's say, different purposes on different, let's say, scales. So all that basically came to this V notation of 3 V's of big data. So volume, velocity, variety. Have you heard about this potentially from the media? No, okay. In the meantime, I think there are 7 V's. Some people talk about the 12 V's. So they extended this with veracity and lots of different elements, more and more. But essentially, the point is that the big data challenge is not just volume. That's really the key takeaway message. So big doesn't refer only to the big in sense of volume. Now, how it relates to machine learning as an example here again in the cloud course and how it affects to computing, we had a little bit in the prologue already, if you remember, where we said essentially if you have larger big data, then your serial computing with statistical computing with R and things you do on the laptop with MATLAB and Octave and Veka and so will all not work anymore. So you have to go to the cloud. And by this, you have to pay the price for it, this training time of, let's say, normal traditional learning models that are maybe, let's say, these days not cutting edge anymore. If you are in the cloud, there are chances that you get better performance really with large neural networks. They are now basically the de facto standard in image recognition tasks and so on. But of course, they need their share in computing, right? They need heavily cloud resources to fulfill their tasks. And this is, of course, another movement of this cloud computing in terms of storage, because the more data you have, basically, if you're swimming in data more and more, the better the models usually are. Of course, it depends on the quality of the data. You can say rubbish in, rubbish out. The quality of data should be okay. But essentially, that's what's happening today. You have more and more repositories. You have more and more resolution in cameras that actually help you with, let's say, bigger data to get better services and better accuracy. So in a way, that's one form of big data, if you want. It's just growing with, all the popular repositories we know. And then when you think about the typical storage, you would say we have this hardware disk, and now we have storage arrays really deep in the cluster archives. So all of this is contributing to the fact that actually it's not so easy to find this data anymore, right? So in former times, you maybe have sorted your data in something called directories, which some people even don't know anymore because they do just apps. So people lose a feeling of directories or files these days. And more the challenge will be to find the necessary data, to have it accessible at the right time. As you know, you always need a good internet connection these days. Usually when you want to do Spotify and listen something, nobody has a pocket anymore, an MP3 player or something like this. So all these topics become now incredibly important. Also, you have seen in the video already very nice facets of vendor logs. The things of interoperability gets more and more a problem. So all the different cloud vendors, they want to, of course, have silos of data to keep you. They bribe you with a very nice offering in the beginning. Everything is for free. Let's say 200 cloud hours is for free, 200 gigabyte is for free. And once you're in, it's very hard to move away, right? And that's, of course, what they want to do to basically get your customer, hooked, we call that, by some nice offers. And then the interoperability, just moving from one cloud to another, is usually very hard. If you think you're an app developer and you actually developed with a Google app engine and everything, and then want to move tomorrow to Albania here in Iceland or to Microsoft, you have a problem. Lots of these services are not one by one existing in the other cloud. So this is a big topic as well. And then reusability is often in different areas of science and engineering, where people have done, let's say, lots of big studies, big climate simulations, maybe of the next prediction in the next 10 years, or human brain simulations to understand better Alzheimer's and so on. And to reuse this data is also problematic, but of course very important for science and engineering, because there we don't have to reinvent the wheel. We don't have to run and burn the resources again, right? We talk about this in FAIR. There will be one lecture talking about so-called FAIR principles of data sharing and data governance and data management. It's a big topic today. Also governed, you see already politically more and more. So people that actually create data, they are forced to put it on open archives. That is fair. And basically open researchers all have to do it these days. So it's a big movement. Another example, when I said about big data in really big terms, is here the square kilometer array. It was actually 1 petabyte in 20 seconds now updated. So of course you can imagine that this is now the challenge, right? 1 petabyte, as I said, is not a problem for data centers. This is easy handleable. But if a data stream comes in every 20 seconds with 1 petabyte, then your silos grow quickly full. And of course, you never know where could be something interesting happening in the sky. So you better keep all the data. Hence, this is of course also the trouble these days of big data, which is not just the volume, but here also a good example of the speed. And then you go through all the, let's say, key advances we have for new adventures. The large supercomputers, if you dump, let's say, a climate simulation very accurately, it is also petabytes of storage. And of course, you make not one run, you make many runs. CERN, LHC, the Large Hadron Collider in physics, they dump a lot of data. And of course, the new challenges will come in the future then in space. Basically, here the International Space Station stands just for, let's say, a placeholder, and we see like what Elon Musk is doing and so on. I think he even agreed now with Netflix to have a streaming of his endeavors into space, which would be, of course, quite interesting. Or if you think what Richard Branson is doing, it's also quite interesting with hotels in space and so on. Of course, there we need to have streaming in and so on. All interesting topics. Now, looking on the storage landscape on big data, how to handle it, there's several different hierarchies. And all of them are in one way or another directly related to costs on the other. So the first thing you have is basically the lowest level, which is lots of tape archives around the world in data centers. This is very cheap data. So there you can have petabytes over petabytes stored. The trouble is, it is taking very long to get this out of the archives, right? The tapes are just very, very slow. And when you have very many, let's say, smaller files like your MP3 collection, you have to done a long migration step to just hear an MP3, right? So this would be not really working in practice, but of course is the most cheapest one and the slowest one. Then you have the magnetic disks, and then of course now the other, not spinning disks anymore, and other, let's say, disks which are all in the hard disk arena, solid state disks and so on. But then main memory is the next step where you say, now it's getting interesting. This is very fast for the CPU, but the pyramid suggests, of course, the costs are already much more higher to have good main memory in the computers and also in the large clusters. So hence there's less from it, right? So you cannot store all your data, for instance, the petabytes we have seen just in main memory to be easily computed. So this is a very much interesting situation. And then when you see the top of the scores, this is very close already to the CPU. If you remember cache, and then also the registers is even within the CPU. These are, of course, the most costly ones, but also very tiny if it comes to the capacity they can work with. Hence, we call this a storage hierarchy, which is, of course, very popular because these days you have to really mix and intertwine all of this to get it working, to manage all the big data facets. And of course, all the cloud vendors, they will have, let's say AWS has a Glacier so-called service, which is more the tape archive, but has also S3 services, bucket stores, and so on in Amazon, which you can use for easy storage, much more easy accessible. But you have to pay the price for it. Of course, now the cents are rolling for every cloud usage, every API call to it. And this, of course, they want to have their money back of the infrastructure they invest. You will also see when we talk about infrastructure as a services, the more main memory you want for your cloud service or for your image that you want to have, or your CPU and GPU for deep learning, the more you have to pay. Of course, they will have a good price on these things, which are so expensive and costly, because this can really make a big difference in your computing to have, let's say, lots of main memory available. And when we talk about this extreme growth of petabytes, we know how to handle it basically on a very slow perspective, but we really have a big problem these days not advancing in memory technologies. So in a way, we basically were sleeping all, and we're basically bypassing the train of improving somehow the memory these days. So this basically is positioning now a so-called DRAM gap, that we don't know how to fill all the petabytes quickly in the CPUs. Right, so the processing units there, it's getting cheaper and cheaper and cheaper to buy CPUs and GPUs. It's getting cheaper to have storage, but the problem is the interconnect, which we have through memory to fill the GPU. And this is actually something where we're not really advanced. It gets a bit cheaper, but if you look on large cloud resources, it's still incredibly expensive and a problem. But of course, here's where the speed is, and where it's very important to understand where the limits of today is. So essentially, we could do very large data centers, but in the end, the trouble is to get to the arithmetic units within your CPU, to the registers, through all the caches, you have to always go via the main memory. And to do this from all the tapes, from the basically hard disk that we have, in a very, very quick fashion. For instance, if you think about big data with deep learning, and you just fuel lots of databases, all the Netflix movies, the user data that people have watched it, there's lots of data available, but it's hard to fill all the different GPUs at once. There are technologies for it that, of course, work and try to work on this a little bit, but still on the hardware perspective, when you want, we have still a big problem in this area, because this cache bandwidth is not really taking shape in memory improvements. And with this, we're having their bottleneck. So there should be some improvement. Some of the improvements, of course, over the years, we have seen that we're going away from, let's say, a small hard disk somewhere. You see the data centers have all large data arrays now. That is something what is happening. Of course, it's much more easier. It's so-called RAID secured. So if one drops out, then it will be automatically basically transferred to other units to protect your data. So also for the security, where we will also talk about in one of the lectures, we are relatively secure. And lecture 4 will basically pick on that, what it means to provide a data center for multi-user clouds today. And then also secure it, which is the main factor, right? If some part of your electricity fails within your data center, you don't want to lose the data. So there are different schemes to this. But yeah, the capacity increase, that's very good. So we see that basically we can keep the data on SSDs. But on the other hand, then also we face more and more the question of the internet. In fact, sometimes it's better to put a big truck, put lots of hardware in, basically all the different arrays of this, and drive to the destination instead of just transforming and basically sending the data over the internet, right? Sending petabytes of data day by day over the internet is just too slow. So it's in fact much more throughput to just fill it, do it physically, which is a bit funny, showing you again where we're sleeping a little bit. And of course, maybe perhaps at least some, Iceland is very good connected, I found, from light cable and so on. That's not the case in Germany broadly, especially in smaller towns. So there's really a big problem running towards us, that we cannot just simply transfer the data anymore. We have lots of data generated, maybe all our nice home with Internet of Things, but we cannot really use it because the internet is needed. So there are some, let's say, discrepancies, not only on the memory side, but also on the interconnects and internet these days. While the storage as such is essentially not a problem, it's just the connection between the data center and the homes, the connection between the different data centers, and then shipping around always petabytes is basically required because we produce just more and more data and use it. But on the other hand, the infrastructure is not fully ready for it. Right, so talking all the time about Amazon, MS Azure, and then Google and so forth. So the, let's say, business and commercial cloud vendors, I also would like to point a little bit to here and there some academic movements you see here, which is basically also something for taxpayers. It's not only purely academic. These are services of the European Open Science Cloud, where basically lots of services are available for researchers to use, from storage capacity up to computing. So this is a little bit different than there. You don't really directly swipe a credit card. You rather say which community you work in, what science do you have, what science data or engineering data you want to provide to the cloud, making it open accessible. And this helps you a little bit, let's say, to get resources for free, more or less, if you're in the right communities. Of course, long term, you have to discuss, if you have petabytes over petabytes, as we've seen in the example with 20 seconds, 1 petabyte, then of course the silos will running full out all the academic centers in the world as well. But still, this is, let's say, a movement to really get the people aware on different elements, how to share data, how to really, exchange data. And the COVID-19 pandemic was basically one of the interesting things. I got also one research project from the European Open Science Grid for COVID-19 chest X-ray analysis. So there's really the mindset of sharing health data now really was growing significantly through the COVID. Especially this is, of course, also important for rare diseases because hospitals themselves, they have just a couple of cases. So they need to unite with others to really have, let's say, the proper data sets. And to support this, to make it basically much more easier, this FAIR directive is also something which is very highly discussed in all the European bodies, the European Commission expert groups, to really put a force on people that get public money, like hospitals in research, or we as researchers from research grant, to put all our data open. Of course, anonymized, pseudonymized, so that their own patients basically, of course, are not exposed. That's not the goal. But still, there's a big movement of reusing this data for larger science purposes. And this EOSC has just many different services, and we will talk in lecture 10 a little bit about it, how you can use it for these elements. So looking now from the storage from the commercial perspective, one of the very famous one is S3. Has someone heard from that? Yeah, it's a very popular service, basically. S3 is the scalable storage service from Amazon. If you're very careful sometimes using cloud services, you can see in the URI for a second or a millisecond that some S3 call gets out. So sometimes you can see that even in the URI. Gradescope was a good example. Some of you know Gradescope maybe from previous years or so. It is relying on S3, puts everything on S3, right? So if you carefully look sometimes when the API calls are in Gradescope, you see an S3 bucket is called. So no matter what cloud services you are, chances are S3 is basically somewhere used. It's a very popular service these days. And how it works is essentially like a bucket you see there. It's just an object store. So instead of doing your hard disk and thinking exactly where's your file and which directory and things like that, you have, let's say, a convenient cloud store where you just put everything in the bucket. You have, of course, a good name, but it's basically decoupled really from a physical existence. It has just some URI somewhere in the cloud, and you can basically these days also nicely integrated in all sorts of explorers, in environments on computers. You have apps accessing it. And with this, you have, of course, very different inherent features of this S3 storage service, right? I mean, basically, it's scalable. So if you need more capacity, you just click and basically get it. You don't have to buy new storage hardware or something, put it to your own service and so on. And it is basically also durable. They guarantee you to deliver 99.9 durability, never 100% in the cloud. I think that's clear in computer science. You cannot achieve that. But at least it's a very high quality of service that they provide. And of course, they do this with different backup strategies, different data centers, and with this can guarantee this. And of course, if you have it as a startup in your cellar and there's, let's say, a flooding that sometimes happens even at universities, chances are that your data is lost, right? It could happen. or some people say volcano is very unlikely, but it happens to have even volcanoes sometimes. So in the end, this durability is often overestimated, but it has some real truths, especially with smaller companies, which actually lose all their data and then are quickly running out of business. And S3 is really a way where you can be almost very, very sure to have it always basically accessible. It goes without saying there are security elements that you can put in. We look in one of our assignments also how you secure different elements of an S3 bucket. And of course, the easy migration, it is something which you see there, different interfaces for development, for basically putting data in as an object store, which is largely characterized that each of the items has, let's say, a key value to find it, some small metadata to describe it, and some, of course, access control rights, if you want, who is allowed to see that. So it's a very convenient service. And the idea is really the scalability, again, by design. Basically there you don't really care, you just pay per use, right? You just use, and then basically that's what your payment in the end in the bill will show. Then, of course, there's this topic what we discussed also the prologue very briefly. It could be that your boss says, well, I'm interested in Amazon, but there's some, let's say, data I don't want to share. So please build me an own cloud, right? And there's some of these elements which are like a Lego box already, again, already existing. If you go to OpenStack, it has really lots of software building blocks for compute, for networking and storage. So in a way, it's a little bit like the Google Cloud, if you remember, with the Google App Engine, all these different Lego bricks and pieces that you can put together to create your own solution. Here, this is completely open source and free. Of course, here you are yourself, your boss. You have to create the cloud, right? You pick the different cloud services, something for compute, something for storage. You see the storage that you have basically as buckets is also available here. Something very similar to S3, but of course you have to configure it. You have to administer it. You have to create it on your hardware infrastructure. But still, the point is to have this, let's say, cloud operating system gives you, of course, the opportunity to do your own cloud solution if you want, or at least in some areas, right? What we have sometimes is, of course, that medical data is then especially stored in these kind of OpenStack clouds, and just some distinct data sets would go out into Amazon because it's very sensitive to share these data sets. But we will talk in lecture 13 about it. It's more like one of the end topics, because of course here it's a very specific way of using cloud computing to create your own cloud. But of course, this is also possible, and many organizations, large organizations, chances are that they run their own OpenStack cloud for several purposes. Now, of course, the area of social networking is very interesting. I think, as we have seen, most of all use Facebook, and those that don't use Facebook, I'm sure use YouTube or Instagram or Tumblr, whatever. These are all, of course, just examples, but have a lot of different challenges alongside, and we will talk about it in lecture 14. One of it is the idea of a more graph-based structure, right? When you think about the bucket store or MP3 collection, you throw that in, and then basically that's okay. The challenge here for the storage is the dependencies, right? How to deal with a like in an instance so that everybody sees it. That is a friend of a friend. This means really performance in graph algorithms. You see that here, how Facebook is actually dealing with this in a database will be one part of it. They actually have different databases for different purposes, for search, for the graph engine, but it is a very unnatural and unhomogeneous growth, right? So it's hard to deal with that in a way. Instead of databases, which always assume there will be new customer, new customer, new customer, or something like this, or bank transaction, very boring, right? Always the same information, thousands or millions of them. Easy to handle because we know what's coming. Here, the growth of the network is completely strange. There's a viral video coming out and suddenly people like it like hell. And the database is, working in this direction or growing in the other direction. So this is really a challenging time for the social networking at large. It's a big, let's say, area of research as well, how to deal with this. Facebook sometimes, leaks some approaches, how they do it. And we will look in it in lecture 14, because only they have really this at scale, right? It's one of the largest companies having such a network all over the globe, owning, of course, also Instagram and all of this. That brings them lots of, let's say, hints how it works, but also lots of challenges and lots of interesting developments. Then the role of scalability and area of networks, we discussed a little bit already. So we pick that up a bit on this lecture 15. So here the idea is maybe not always pull the data again on the network and back and forth, but maybe there's some smaller computing you can do locally before you essentially always transfer it back and forth between the data centers. This is something we call big data analytics framework. So for instance, Hadoop was very popular for this. This is so-called MapReduce paradigm, where you try to avoid all the transfers and just do smaller map and smaller reduced computing tasks, basically locally on smaller computers, aggregate the results and then send the aggregated results back. So this will be a topic where we also have an assignment on reaching to technologies like Spark and basically Hadoop, which are very popular frameworks. Interestingly enough, you see that was invented by Google in 2004, almost a time where Google was still better. I mean, do you remember these times? Maybe still a search engine which says Google better. It's unbelievable these days because they rule the world almost. It's incredible what this company has basically had done in terms of technology advancement. And what you see also, they regularly also participate in the sciences. So this MapReduce was really coming out from them and showing how to deal with these large quantities of data they had at that time with a Google search engine. And now, of course, the technologies all advance in different directions, in more memory usage with Apache Spark. And this is all what we talk about it. So another element with this is this big data analytics. You have heard from this maybe in the news, big data analytics, job advertisements, not yet. Okay, so this is something which also was very happy at that time and starting to be emerging, where you basically use all these different data sets for analysis, but in a more technical way. So you don't do normal data analysis with statistics or something like this, but here really aggregate information and try to make a meaning and put a meaning out of this. I have an example for you essentially very soon, just that you understand the differences. So often data analysis is really related to causality. So there you basically have a concrete data analysis problem, you use proper statistics or machine learning, you analyze the data and you have, let's say, a reasoning after this. This is a very important aspect in it, because essentially what you have, unfortunately, in many of the big data analytics activities, you digest a lot of data, you look at lots of things and they correlate, but they might be not really causal in any dependency, right? So this is often the case if you use very big data sets and, you know, do a, let's say, not really direct data analysis, but just more aggregations and so on. And then you have some certain bias in it. And we talk about this in lecture 5, also again about the differences. Of course, you would also use big data analysis with some of the big data analytics data. They are a bit intertwined, these topics. But on the, let's say, 10,000 feet perspective, you see essentially here that there's a big difference. However, causality takes very often time and goes also into directions where you then have always wrong models or so. Maybe you don't get, let's say, results quickly. In data analysis, you basically have often results very quickly. When you think about in data analytics, you have the results often very quickly. And this, of course, is one of the benefits, again, from these analytics, showing you already trends where maybe data analysis takes some much more longer months to establish and basically to find the reasoning behind it. One of the most famous, I think, approaches there and errors in this was basically the flu at the time of 2009. You remember there was another flu, another pandemic called H1N1. It was not COVID-19. But people have then, they are very exciting that basically there was really large data sets that could be revealed and could be looked on. And of course, Google at that time was really exploding, right? So they started with being the #1 Google search engine of choice. There was no Yahoo anymore, just tiny and things like that. So this was growing. And Google basically had the chance of really predicting what was happening around the globe much more quicker than governments. Right? Governments have to pull out the information from all the different medical directives, bottom up through all the medical health centers, takes 3, 4, 5 days to get a proper trend. So Google just looked at the data one evening. Okay, that's what the trend is in the data. So this was the idea, and it was, of course, very exciting because people have seen, oh my God, here's someone searching for the flu. There's something for the flu. So they have probably symptoms. Right? It's not data analysis. This is now the wrong factor in it. This is just a correlation where people searched, okay, there's H1N1. And it's basically, is of course, a high likelihood that they want to know something about it. It does not necessarily mean that they're themselves infected. And in fact, this paper was a big debate, also how slow governments sometimes are and so on, and how big companies taking over the globe and all the information. But you see also a couple of years later, this was really also analyzed. And in terms of this causality, what I just explained. So you have lots of challenges with this data analytics very quickly if you don't do it properly. The one is basically the data set transparency. The Google search data was basically switching every day, changing significantly how people actually use a search engine. And analyzing this, of course, makes it not really transparent if it changes. And you can also have no causality, no reasoning for it, because the database always change. And then the algorithm they used at that time was also quickly changing. So there was MapReduce with some smart algorithms together, and they improved the algorithms, new parameters. And then suddenly there was, let's say, another region highly infected with basically the pandemic or with the flu at that time. And then the data quality and so on, there were many other factors which actually showed that data analytics on the other side has to be very carefully looked at. One promising example was that many people in the United States were calling a lot from the West Coast to the East Coast, and then basically informing them, I have this H1N1, and they search it, but they don't really are infected just on the other end of the coast, just because they are always on the phone at that time. You largely find not an American that has not his mobile and talking to relatives and so on. So essentially, this was all influencing factor, making essentially this parable of the Google flu at that time. And this, of course, shows you also the idea to really look careful on data. That is also explains why sometimes we have to wait for results for COVID-19 a bit, because people are very careful these days what they predict. And usually we always would say it's nice to have it very quickly, of course, and with lots of correlation. There's one very famous one, you know, if you heard from Hamburg and the basically birth rates of some birds. Oh, someone not heard from this. So there's really a directly correlation of babies and of course the birds that bring babies. So it's really in a couple of years really trackable. But of course we know already that this is not a really causality, right? But it's a very good example of correlation. The data shows it one by one. So the more birds of this type, the more babies there are. But we are basically educated and know that this could be probably not happening. This is just another example of this data analytics, very easily correlated, but not necessarily in causal dependency. Good. Looking more then from the cloud and technical side, how we deal with those big data sets and also how to avoid maybe the transfers, as I was explaining. So maybe do it a bit more distributed, locally processing. We have this framework called Hadoop, which is basically very known as the MapReduce implementation that is open source. We will start with this very early on in the course, including also Apache Spark, which will be your first assignment in MS Azure, we talk about on Thursday. So, but both are basically an evolution factor. First was Apache Hadoop, and then over time, Apache Spark evolved. Of course, here you see very nice things that, of course, Hadoop is very slow and Spark is very quick and so on, just by logistic regression. This is a specific machine learning algorithm we will talk about actually on Thursday. But the point is also Spark has in-memory computing. So it's a bit unfair to really compare it one by one, because here also the costs in the cloud are higher because you need a high memory machine, a machine with lots of memory footprint. And these are things we talk about then when we look at the MapReduce frameworks, which underlie basically these elements and come to this problem of MapReduce, where we really chunk a problem into different pieces, try to solve some of those locally without big network interconnects, and then merge and shuffle and basically bring that together to one solution that you're interested in the result. Some people know that from computer science. It's a principle of divide and conquer, which essentially is also the MapReduce paradigm, a little bit, of course, a bit on steroids and a bit tuned, but the basic idea is essentially the same. Right, and then the networking impacts. Of course, here we have different requirements also from the storage side. We will talk about this also very soon now, where you need reliable file systems. A Hadoop distributed file system is, for instance, one which keeps different replication strategies, just to be sure that your data is not lost. We use the Microsoft Azure HD Insight, which is also a nice infrastructure, which will be coming also on Thursday and what we will discuss. We will use from Spark several elements. You see Spark on the top has also some interesting different libraries we're going to use. One is the MLlib for machine learning implementations of algorithms in the assignment. And then we were basically thinking about these different machine learning and statistical data mining tools. This will come already on Thursday. I know that nobody of you maybe has a big overview of this, but we will start with a very low-level introduction of machine learning, just to get a feeling for it and a handle for this, to use it with big data, to use it with clouds, give it a meaning, right? We want to do something in the clouds which makes sense. And here, of course, these methods that you see there, classification, clustering, regression tasks, are one of the ways of how to make meaning out of big data, how to use big data for some specific purpose. Just a short overview. We said classification tasks are usually that you have already groups existing, you have a new data item that comes in, and then you want to know which class it is, and you can do so because you have the class existing. One is that basically you don't have any classes available, you have just similarity. You would say those are closely together, so maybe they form a class or a group, something we call clustering algorithms that bring classes out basically aus basically unlabeled data. And then some trend analysis, various regression tasks, and so on will be also part in lecture 2. Right, mostly we talk here in the course supervised learning. This is an area where you basically have always a guiding label, so to speak, for all the images that you see. So someone has already told us here in this image, it is an Iris Virginia or it's an Iris Setosa. When a new data set comes in, a new image comes in, we want to know which class it is, but we can learn this over time, basically by having this labeled data set. In unsupervised learning, that's not the case. It is more like the clustering we have seen here, like in the brain images. When you have, let's say, different cells together, they form a certain cortical layer in the human brain. This is just on density and similarity measures. There's no really guiding label. And then reinforcement learning is another category where we basically have also not really big elements in it, just, basically for your sake of completeness here. That is basically how humans learn, basically always by try and error case. Good, yeah, so this is something what we will have also on Thursday. So here we can go a little bit quicker. We will tackle Apache Hadoop and Apache Spark, and this will be something for the first assignment. Here we will use the MS Azure Hub. Oops, sorry, this was a bit quick. So was just one slide left. And then, of course, we will go a certain recipe again, that you basically see how to use a cloud over time for solving your problems. So this will coming back when we have all our different assignments. So I will play the video just for the sake of the recording and for YouTube and all of this. But basically, you can see that also at home, so there's no point of maybe necessarily staying here unless you have a question. Otherwise, we see us on Thursday. Thank you very much.
Banks face many challenges as they strive to return to pre-2008 profit margins. These challenges include reduced interest rates, instability in financial markets, tighter regulations, and lower performing assets. Fortunately, banks taking advantage of big data and analytics can generate new revenue streams with personalized offers, targeted cross-sell, and improved customer service. Big data and analytics provide more insight by analyzing a higher volume and variety of data types from more sources than ever before. Deeper insight by digging deeper into customer information and behavior, enabling segment of one marketing. And faster insight by performing real-time analysis of customer information to deliver offers at the point of decision. Big data and analytics can analyze many types of customer information, including spending patterns, behavior, channel usage, product portfolio, bank interactions, credit information, social media, and customer profitability. Here's a day-in-the-life customer scenario as an example of big data and analytics in action. Peter is a customer of leading bank with a mortgage, checking and savings accounts, and a line of credit. Peter is remodeling his kitchen and decides to buy a new set of chef knives. The bank recognizes that Peter has made a number of household purchases lately and analyzes his financial and transactional data, including spending patterns, income, savings balance, available credit, loans, credit score, and level of risk. The bank also analyzes his related activity on social media and learns that Peter loves to cook. He enjoys gourmet restaurants. He blogs about his dining experiences and indicates he likes a new restaurant-style gas stove. Using big data capabilities and predictive analytics, the bank anticipates similar home purchases, but knows that Peter is nearing his credit limit. The bank wants to seize this business opportunity before Peter is offered a credit card from a retailer. The bank sends Peter an offer to extend his line of credit. He uses the additional credit to buy the professional-style stove for his kitchen. The banking system also identifies this as a large purchase and prompts Peter to take and archive a photo of the receipt and warranty. As well, the system recognizes this as a home appliance purchase and offers an extended warranty to Peter based upon his zip code. It's now 11:30 a.m. Analyzing Peter's regular lunchtime purchase behavior and preferences, the bank sends him a personalized offer from one of leading banks' nearby merchants, Chefwich. The system prompts Peter to share the offer with his friends through social media. As Peter pays his bill, the bank sends an alert to verify that he has authorized the purchases made today, preventing fraudulent charges to his account. Later, Peter logs into his account with his tablet computer. He looks in My Offers to find his personalized offers. After analysis of his spending patterns, the bank suggests that Peter sign up for their Smart Sweep service. Peter also sees a home equity line of credit offer based on an analysis of his financial condition as well as information on his home from third-party sources. Finally, the bank recommends that Peter sign up for overdraft protection to avoid the frustration of any future fees. While Peter is logged into his account, he also views the Spending Manager feature to gain insight into how his spending changes from month to month. Peter can compare his spending to financial peers in his geographic location, income, and age bracket. With new capabilities provided by big data and analytics, banks can develop new products and services that help customers manage their finances and save them money, deliver relevant services and offers that fit seamlessly with customers' daily lives, improve the customer experience, and promote customer satisfaction and retention, and at the same time, generate new streams of revenue for the bank.
So that's it for today, also for the online audience. That's all for today. Thank you very much for joining. Just the remaining lecture bibliography, and then we see us basically on Thursday.
Okay, thank you for your class.
Thank you for joining. See everyone.